side on me at the same time. I'm in the daylight, calling to say hi. But your words if there's something that you need to say, I know it ain't easy living inside your brain for sure. You keep telling me that it's all okay, but I know, yeah, the silence speaks so loud. The silence speaks so loud. Tell me that it's all okay, but I know the silence speaks so
Hey everybody, happy Thursday. How you doing today? We've got to talk more about recursion today, and then I think we're good. Let me double check. I think that's all that's on the schedule. My screen is being really screwy right now. I don't know why. I'm losing like the top inch here on anything full screen, but should be okay. Yep, recursion, and we'll do our lab next Monday on recursion, and then talk about plotting next week, and then we'll have time. We can do a plotting lab just to get some practice in, and then that final project is coming up. So if you do have any questions on that, let me know. I'll be around to answer those for you. All right, so with recursion, we looked at a couple basic examples, and these ones are all essentially just a loop, where we're just using the recursive function as a loop. So we're going to look at a different example today. So let me add a new file here. Call this one the maze solver. So with the maze solver, this one is not just a simple loop. We're going to be actually trying to do this backtracking recursion to solve a maze. And let me draw one here real quick for you. And the idea is we can come up with an algorithm, right, the sequence of steps that will eventually solve a maze for us. So if we were to just draw in a simple little maze here, and we can imagine this is like a 2D list, right, with rows and columns. And it doesn't even have to be square, right? That's okay if it's not. Maybe you have X's for walls, right? Those are places you can't go, and on and on. And oops. Maybe we'll put an S for start and maybe an E for end, and you have to get from start to the end. And the idea here is we need that sequence of steps that we're going to do. So what we're going to do is we're going to see, is there a base case? Right? How do we know if we're done? What's the simplest this problem can be? There's actually two different base cases. The first one, hopefully is obvious, is when we get to the end. If we're standing on the end, we win. We're done. Right? That's one base case. The other base case is we get stuck and there is nowhere to go. Now, in this case, there's no dead ends, but maybe if we were to like put a dead end here, you can imagine if we're traveling up the maze to here, that'd be a dead end. That's a base case. So it means that's no good, can't go there. And what do we do to simplify? Well, we take a step, right? We take the complex problem is, well, I haven't solved it yet, so let's take a step. And what we do is you have to tell it, this is our dead end. We have to tell the maze what direction we want to go. So it's pretty easy if you say, let's go up, we'll go down, we'll go left, there's an end there, and then we'll go right. Up, down, left, right. Okay, and we're always going to do it in that series of steps. So what we're going to do is we're going to start here at start, and we're going to say, can we go up? No, we can't go up. All right, can we go down? Yeah, we go down. So now we're here. Okay, and then we're going to start. Can we go up? Well, if we go up right away, we know we're going to have a problem because we're just going to be up, down, up, down, up, down, up, down, up, down. We'll be stuck. So we're going to leave breadcrumbs as we go. And if there's a breadcrumb, we're not going to walk on top of it because you've already been to that square. So we're going to say we can't go up. All right, let's try down. So we go down. All right, now we're here. Well, we can't go up. There's a breadcrumb. Let's go down. Okay, now we're here. Okay, well, we can't go up. There's a breadcrumb, so let's go down. Now we're here. We can't go up. We can't go down. We can't go left. We can't go right. That's a dead end. So we want to mark that as a dead end somehow. And maybe we just put a, I don't know, what do we want to do? How about a D for dead end? Excuse me. Sorry, this cough has been terrible. And then what happens is we start unwinding, right? We tried all of these steps, and we go back to right here where we had just tried down. Remember, each one of these goes on the call stack. So at 0, 0, we go down. At row 1, column 0, we go down. At row 2, column 0, we went down. At row 3, column 0, we went down. Right? 0, 1, 2, 3. And at 4, 0, we couldn't do it. So that one comes off the call stack. Now we're at 3, 0. We just tried down. Now we're going to try left. We can't go left. We're going to try right. And then we just keep adding to the stack. Now at 3, 1, we're going to try up. We're going to try down. We're going to try left. We're going to go right. And you just keep adding onto the call stack as we go. So eventually we'll find a solution to the maze by doing this backtracking. So if we hit a dead end, we just go back. We backtrack to the last place that wasn't a dead end. Okay? Excuse me, I gotta mute a second here. Sorry. Oh, whew. Sorry. Okay. So we're gonna write a little class for our maze solver. Maze solver. And in the init, if we accept the maze, it'll be easy for us to just have it. Otherwise, we have to do some sort of input stuff. And remember, anything that's input should be outside of the class. We're going to say myself maze equals the maze, and we're just going to assume it's a 2D list. And then we need to go find where we start. Right? We need to know where the starting position is. So for, I'm going to say row index in range length of the maze. And then for maze at row index, for column index in the range of the length of the maze at the row. So the idea here is my row might be a different length, right? The different number of columns than I had rows. So this will make sure we're always ranging off of that second dimension here. Then I'll give you my column index. And say if the maze at row index at column index equals a s. We know what the start is. We'll have self dot current row is the row index and self dot current column is the column index. Okay, done. We'll go and set those values. We know, and maybe we make those private, sure. So don't mess with those. Okay, so now we know where to start. Oh, 2 equal signs there. Equals the starting character, s. Okay, and then what we have is we have the recursive method, solve. And solve needs a row index and a column index. We could even do without that because we're tracking it here with self. So we'll just solve. Perfect. So we'll solve. So we'll say if self.maze at the row index, that's self.row index at self.column index. Oh no, sorry, that's current row and current column. Got to use the right variables here. If that one is equal to the end, then we won. Game over, right? We solved the maze. That's our base case. So maybe what we'll do is we'll print self. We'll figure out. We'll do a little define a string where we can define this string function for self. This is how we turn ourselves into a string. Let's say for row in self maze. So we have a output is blank for now, and then we'll take our output and we'll add in there the row.join, or what? Nothing.join the row, and then add in a new line. We have to do our own new lines here, \n. So we're going to join all the characters in the row together, right? We don't want any special characters, and then we'll return the output when we're done. So I think that'll do it for a maze. Excuse me, guys. Okay, so if we reach the end, we're done, right? If we didn't reach the end, right, our else case here. Well, let's try. Let's try going down or up, down, left, right. So we're going to check to see if we can go any of those directions. So we probably want a little helper method here, right? Like can go to a row and a column index, row index and column index. And what we can do here is we're going to return the row index, a couple things, right? Because we need to check first that it's inbounds, so we don't want to step outside the maze, and we want to check that it's open. So we're going to first check that it's inbounds. We're going to say that 0 is less than or equal to the row index is less than or the the length of self.maze. Right? So make sure that the row is good, right? And that the column is good. Same thing with the column. Column index. And this time we want to check the maze at the row index. Make sure we're checking that column. Make sure the length is good there. So that means we're inbounds. Then if we're inbounds, then we can check that self.maze at row index at column index. What is equal to open? Backslash, there we go. We make sure that it's an open space. And then I've done this a couple times. We're going to also run into trouble if we aren't careful, because we also want to be able to land on the ending space, right? So it's open or end here, right? Because those are both valid spaces for us to go to. Either it's open, right, indicated by space, or it's the end where we want to get. So we can go. Okay, so that's how we can check if we can go there. So what we're going to do is we're going to check. So we're going to try, right? This is up. We'll try down. We'll try left. And we'll try right. So we're going to say if self.canGo, right? Can go to, and now we're going to take our self.currentRow -1, because that goes up, right? If you go up a row, and self.currentColumn, current column, that one stays the same. So if we can go up, let's go up, right? So what does going up mean? Well, the first thing we want to do then is we want to put a breadcrumb, right? And we want to do this every time. So we're going to take self at maze is equal to, we're going to change it and put like a little breadcrumb in there, right? Good. So we put a breadcrumb in our current space. Then we're going to see if we can go up. So if we can go up, great. Now we're going to recurse. We're going to call solve. But before we do that, we need to change current row. We're going to take self.currentRow -1. Right, so we'll change the current row, and then we'll recursively solve. So, and we probably also want, let's, that's okay. And we're going to do this again for down, and we're going to do it for left, and we're going to do it for right. So, but for going down, that's row +1. For going left, that's column -1. Right, and for right, that's column +1. Right, so if we kind of walk through this again, excuse me, we're going to see if we can move until we find the end. But what we're not doing is we aren't marking the dead ends yet. So if all of this runs, right? We try solve, we try solve, we try solve, we try solve. We can't go up, we can't go down, we can't go left, we can't go right. Remember when we get to this dead end? So we went down, we went down, we went down, we went down to here. We can't go up because there's a breadcrumb. We can't go down, we can't go left, we can't go right. We need to mark it as a dead end. So if none of these work here, right, then I'm going to mark self.maze at the current location as a dead end. We'll just put a D in there because it was no good. Okay, we've tried all of these things. We're unable to solve it. Okay, but what also has to happen is when that unwinds, right, we come back up. So we went in the call stack here, we went down, 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 down a bunch of times. So we got to this step here, line 23, right? At 0, 0, we went down. At 1, 0, we went down. At 2, 0, we went down. At 3, 0, we went down. We got to 4, 0, couldn't go anywhere, so that method finished. We came back to the 3, 0 down. So we need to undo this step. So if we come back from solve, we need to undo the thing that we did. So we're going to put the row back. Right? Because that way it can keep going back on to where it was before. So we're going to undo this here. So this is the undo the change step as we're unwinding that recursive call. Right? So from 4, 0, we got to here. We need to change it back and put us back at 3, 0. So that way I can check to see if I can go right and left. Okay? So it'll unwind. And then it'll try. And it'll unwind and it'll try. And it'll unwind and it'll try. Why doesn't it like that? There we go. Okay, one space. Okay. So we should see if we can solve the maze then. So we need to go import. That's fine. Maze solver. Or from maze solver. Import maze solver. I'll zoom that in a little bit. Okay. So I'm going to comment out these prints here because we don't need to be printing all these, right? Okay. We'll try the maze solver. So let's make a new maze, right? So we'll say maze equals a 2D list. And let's see. So let's do a start and a space and a space and a space. Okay, let's just do a couple of those. So just a little maze. Space, space, space. Okay, we'll put the end over here. And we'll put some walls in here. X, X, X. Sure, that ought to do it. You know, I'll put a couple more walls. All right, so if we're going to go down, it's going to fail. We got to go right over and over. And we'll see if we can get the maze. We're going to create a maze solver. My maze equals maze solver. And we're going to hand it the maze. We gave it. And then we're going to call my maze.solve. And see if we can find a solution to the maze. Here we go. Right, 3 dead ends on the way down. Breadcrumbs over this way. We did it. We found a solution. Cool. Now what if there was more than one solution here? What if we had a space there? What do you think we get? Right, well it goes down, 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 over, over, down, over. It found it, but then because we left breadcrumbs here, right, it marked these ones as a dead end, that path, because we had left the breadcrumbs. Found our solution, but then we couldn't get there anymore. Right? So as we were leaving our breadcrumbs, great, left a breadcrumb, and then we tried. We left a breadcrumb and we tried. If we got to a dead end, we marked it as a dead end. Cool. So up, down, left, right. So it's going to try up, down, left, right, up, down, left, right, up, down, left, right, dead end. And then it goes right, right, and then it tries up. Oh, that's why it was a dead end here. That's right, because we tried up, up, that way. That's right, so from here we tried up first, and we reached a dead end. That's what happened there. Okay? Any questions, guys? So this one would be much harder to do without recursion. It's doable, but to be tracking all of this is not just a simple loop. Right, and hopefully you see that, because we have all these values that are changing, right, with our current locations and whatnot. So you have to be careful. So just because we can solve it recursively, it does mean you can solve it iteratively, but it doesn't always mean that it's easy. So in the case where it's just a loop, yeah, it's usually easier to just do the loop, and the loop's going to be better for you anyway. But some things like this, it's harder to do iteratively, and the recursive solution is nice. Now, it does get into trouble if we have really big mazes. We can write really big mazes, and it can get into a little bit of trouble, but not too bad, because it's going to try every single path. So if your maze is like 1,000 by 1,000, we're going to have a lot of, we could go up and down, up and down, up and down, and we might be able to run out of that, the recursion, we might exceed the recursion depth. So there are definitely better maze solving ways to solve mazes. This is just a simple recursive backtracking solution. I like it because it illustrates the recursion, but it's not a smart maze solver by any stretch of the imagination. It's a dumb solver. All right, that's all I've got for recursion for today for you guys. Again, we're going to hit this next semester. We'll do a little lab where we practice one of these, and then next semester we'll do another project with recursion, and we'll get a little deeper into it and look at some of those other ways and other cool things we can do with it. All right, do you guys have any questions? The inheritance lab. For the curved assignment, yeah. So with that one, we have. I don't know. I think I probably just need a reboot here. Let's see. There we go. So this one here. Right, so our regular assignment here, yep, and then curved assignment extends. So you're looking at what you should pass through. So like you should get average, max, and min, but they all get adjusted by that, whatever the difference between 100 and the max was. So add score is perfectly the same. You still add all the exact same scores. So we don't need to change that one at all. But to get average, get max, and get min, we need to find what the difference is between min and max. And then we need to add that to whatever we were originally getting here. So we're going to call our superclass's version, and then we're just going to add that adjustment. Does that make sense? Excuse me. You want to see it real quick? We can do it real quick. All right, so we have a class for assignment. And we have a self dot, I don't know, what do we call it? Scores maybe? Equals a new list. And then we can add a score. We'll take self scores and we'll append the score in. Okay, and then a get max score or something, right? We return the max of self.scores. And a get min score. Returns the min of self scores. Oops, in there, and then an average, right? Get average score. So that's the sum of self scores divided by the length of self scores. Right? So that's assignment. Cool. And then we're going to write a curved assignment, right? So what we called it? Curved assignment. That extends assignment. Right? So it is an assignment. It does all these things, but these need to behave differently. So what we're going to do is we're going to add in a method here to find what the, I don't know, we'll make this private probably, get adjustment. And we need to find the max score. Okay, that's self dot get max score. Oops. Actually, we want the super version of get max score. So we want 100 minus that. Right? 100 minus the max is whatever that adjustment is. So when we do these versions, right, we're going to take the max plus our get adjustment. And really, we don't even need to do them. I mean, sure, whatever. It's get max score. It's probably cleaner to do these supers. Get min score plus the adjustment. And super get average score plus the adjustment. Right? And that's it for curved assignment. We're just changing the behavior here to say, okay, do this, but then add that adjustment in. So then if I make a curved assignment, first assignment or something, whatever, equals a curved assignment. And then we'll go add some scores. Add score, we'll add the 70, 80, and 90. Right? So super says do your parent class's version. So because I want whatever they were doing for get max score, I don't want my version of it because I would call myself again and call myself again and call myself again and call myself again. I want my parent class's version. I want the super class's version here. So it'll run this get max score with super. That's how we get the parent, because we're overriding here, but I still want the parent's behavior. I just want to customize it a little bit. Excuse me. So we add some scores, and then if we print first assignment dot get average min and max. Or I don't know, we'll do min, average, and max. How about that? Get min score, get average, get max score. Okay, so we should get no longer 70, 80, 90, we should be adjusted to 80, 90, 100. Because we're adding in that 10. Right? Because that was the difference between the 10 or the 90 and the max. Right, does that make sense? And then, so unit tests again, like you would go and just test that you got out the right scores. I just did it here in Maine because I was lazy. Sorry. Nope. I don't know what I'm doing here. 2020. How could I forget what year it was? So let me do Lab 9 first. Push that one out there. And then we'll do our maze solver. Okay. Cool. You guys got anything else? It's been weird not seeing you all semester. But it's 2020, I guess. Oh, a dad joke. And I haven't done one of those in a while. Thank you. Let's see. Oh, I just had a good one. My kid's got my phone because he was watching YouTube on it. What was it? It was a really good one. I liked it. Let me go see. I'll get you one. Give me just a second. I gotta go find it. Yes. I learned the other day that trees poop. Right? Just like other animals do, trees do it too. I mean, where else do we get number 2 pencils from? There you go. That was a pretty good one. I was quite fond of that. I get a lot of them off of Facebook. There's a whole premium dad jokes page you can follow, which is fantastic. My friends send them to me because they know I'm corny. All right, gang. If you got nothing else, go get started on that final project if you haven't yet. If you got questions about it, let me know. Again, try and build slow and small. So start out little piece by little piece by little piece. So don't worry about doing all the tracking. Let's just see, can we make it play war from beginning to end? And then we'll see, maybe now let's count the turns, and then maybe let's see if we can change the deck, and then those sorts of things, right? So start slow with small pieces and build on it and build on it and build on it, okay? And we're going to see what kind of relationship we have between the number of cards in the deck and the number of turns. All right, guys, it's been fun. Take care. Definitely let me know if you want to chat. I can fire up Zoom, or we can do a Discord call. I'm happy to talk with you guys and see what's going on. If there's anything I can help with. And don't forget Zybooks. It is coming up due. If you are behind on it, you're just making a pile of work for yourself. So do try and keep up to date with Zybooks. I guess take care.